Hi everyone, this is GKCS. In this video, we are talking about Amazon DynamoDB, which is a paper from 2022. DynamoDB is a very popular NoSQL data store. It has over 1 million customers. I don't have that many subscribers as these guys have paying customers. They make around 79.8 million requests per second at peak load. So this is easily about 10 trillion requests daily. One of the main reasons why it's had such popularity is because it's very easy to set up and it provides auto scaling. It's a NoSQL data store. It easily stores petabytes worth of data, sometimes with a single client. Now the funny thing with this is when you see NoSQL, you might think, oh, asset guarantees go out the window. Eventually consistent. No, DynamoDB says, let me be a contrarian. Let me say that NoSQL with asset guarantees. So you can have transactions in DynamoDB. The C here is basically serializable. Another thing that we mentioned is eventual consistency. Yes, that is something that DynamoDB provides, but it also provides strong consistency if you need it. So most users who would have otherwise left you saying that, no, I need a strongly consistent database, no longer have that excuse. And finally, there is a clear bias towards having consistent behavior. This is one of the craziest parts about Amazon. It has not that much to do with tech, but with their culture, that if things go wrong, they go wrong in a predictable way. If things are going right, they will be happening in a predictable way. So if users see that a page takes 5 seconds to load, that is slow, but it is bearable. What's not bearable is the page loading sometimes in 100 milliseconds, sometimes in 3 seconds, sometimes in 4 seconds, sometimes in 10 milliseconds. Okay, so the variance is something that Amazon DynamoDB is completely against, or basically the engineers at AWS don't want to see. Now these 6 points make DynamoDB very interesting to study. Now let's look at the request flow of DynamoDB. You have a client, which is just behind my head, and the client is sending a request to a request router. This is one of the interesting things about Dynamo, which says that let's isolate concerns. Let's say request routing, load balancing is one thing, you have it here, and storage is another thing. So you have separation here, but in reality, they are belonging to the same availability zone. Okay, so one request router can send the request to the same availability zone, or depending on where the primary of this key is, you can send it to a different availability zone also. Okay, so typically what you try to do is you want the client to connect to the request router which is in the same availability zone as the primary, but sometimes that may not happen. Just to ensure that it doesn't cause any issues, you have a separation. Now, when the request router gets this request, the first thing it does is query a cache. This is a global distributed cache called memds. Memds finds the SSDs where the key belongs. The request router now sends it to the primary. Let's say it's here in the same availability zone, which persists the data and then forwards it to the other two replicas for this key. Behind the scenes, you have some special stuff happening, which is the SSD stores the data, but at the same time, the data is replicated to S3 using logs. So this log is streamed into S3. Now, if you're looking for backups, replication of the data, all of that can be managed here itself. In fact, if you're looking for a change data capture solution, or if you're looking to do something with that data, if you want to stream that data, then that can be done easily using DynamoDB streams. So the data changes or the logs can be consumed by the client through these streams. There's other benefits of the stream also. For things which require eventual consistency, streams do really well. One of the things is indexing. The index is created using stream data, which is eventually consistent. Now, if the user wants a global index saying that get me all the users in a particular department, so by this department ID, it's possible that department ID is not a sort key or a partition key. Doesn't really matter. All you have to do is go to this global index on the department ID and it will store the data in a way that the department ID will be used to sort the data, and there'll be a copy of the data from the original tables using these streams. Now, one of the funny things about this architecture is when a client makes a put request, it goes to this request router and it finds the primary, persists it there first, and then replicates. Before the replication is done, can you do a get request? Let's try. If you do a get request with eventual consistency, it will go to the request router. It will see that this SSD has persisted the request, or it will order the request in a way that the SSD will have to process it after persisting, at which point you can get a response, which will be strongly consistent. If you're going for eventual consistency, the request router may also send it to one of the replicas for load balancing purposes. In this case, the data is not replicated yet. You're going to get slightly stale data, slightly old data. It's possible that the data was already deleted here, but that tombstone did not go here. So you might get something which has come alive again. Okay, so this is possible. Eventual consistency is what you're going for. But if you force strong consistency in a get operation, then you are guaranteed that the request router is only going to send it to the primary. Because all writes happen in the primary, the reads which will happen subsequently will be sure that the data will be the most consistent value. And the way that you elect these leaders is through multi-Paxos. This is a leader election algorithm, which is a variation of Paxos. The leader has a B tree which has all the keys sorted and easily indexed. But it's not necessary that all its replicas will have B trees. It's not important for its replicas to materialize the view. So if you do a read request here, then it's going to take a long time to read, because if you're reading through logs, it can be order n. So ideally you want to send the read request to replicas which have B trees with them, a materialized view. But this is helpful because if you're looking for higher durability and persistence, then a replica with just logs is sufficient. Okay, in this way, you're able to reduce the amount of work that these replicas are doing, which improves write throughput. Speaking of logs, the logs that you send here are propagated to the streams service. These changes are extremely important for DynamoDB because their replication, their database replication often depends on this. So what they've done is verify this with TLA+. This is a formal verification method. So they're sure that their changes will be propagated. And in this high-level design, there's one thing which is much more complicated than it initially looks. Guess where that is? The cache. This tiny cache is actually quite complex because it's in the critical path of any client request. Whenever a request router is looking for a SSD to persist the data in or to fetch data from, what's really happening is it's first going to the cache and getting the primary, getting the replicas that it needs to query. The cache is usually populated with a 99.7% hit rate, which means all the requests almost successfully go to the cache. In case there's a failure, you pull from the data store. What if there is a failure? What if this cache has gone down and it is being repopulated right now? It's a cold cache, it's going to get warm in some time. The success rate goes from 99.7% to 0%. Why is this such a big problem? Earlier, if you had 1,000 requests, 997 were being answered in a very short period of time, let's say 1 millisecond. And now all 1,000 require the long period of time, which is, let's say, 10 milliseconds. So earlier your average request latency was, for all intents and purposes, 1 millisecond. Now it is 10 milliseconds. You're going to be able to handle 1/10 the request that you could earlier, which means your request router is going to be bombarded with requests and it's going to be performing slowly. The entire request path is going to be affected and your system can come down. To avoid this, the crazy thing that AWS does, I really find it is insane, is to actually keep the client cache querying the DB from time to time. Whether you find a cache hit or a miss doesn't matter. The client cache will keep querying the DB and getting the latest data from time to time. Now why? If you have the data in the cache, why are you querying the DB? The reason for this is because you want consistency in the amount of work that the cache is doing. So if requests start getting slow on this cache, you start responding by scaling up the cache. Okay, so you add more servers. So earlier you were able to manage with 10 servers. Now you see that your request load has increased, you go to 20. If you had a massive cache hit rate, then you would say, I can manage with just one server. Later on, you would scale to 2 servers, but when there would be a crash, you would need 20 and you wouldn't have 20. You couldn't bring up so many cache nodes quickly. So just to avoid a shock, you have caches constantly querying the DB, doing more work than they need to, so that you can monitor them carefully and scale them to the right level. Okay, like I said, you are trying to make a boring system with very low variance. Caches actually increase variance, and AWS is known for reducing variance, increasing reliability as much as it possibly can, and that is embodied by this cache. AWS should be sponsoring this video. I'm speaking a lot of good things about you. The data schema of DynamoDB is quite simple. Every table has a partition key, which is used to horizontally scale DynamoDB. When you put or get any data from the DynamoDB table, the partition key is used to find which partition this data belongs in using a hash function. This is very similar to a hash map. You also have an optional sort key. This is similar to an index in a relational database. The key can help you quickly search for elements using binary search, and also range queries become efficient. Together, they make the primary key of the table. So the partition key plus the sort key combined is one unique key. Let's take an example where you have posts being made by users. So let's say Reddit is using this table to store posts, and the partition key is the post ID, while the sort key is the timestamp. With this table, you can quickly find all the posts in the last 7 days by querying all 3 partitions and aggregating the results, which are sped up due to the sort key. You can also query for a specific partition. So for example, if you know that all the posts in India are going to the partition with post_2 as a prefix, then you can get all posts in India within the time range. You can also use more advanced design patterns. So for example, if you want to find the latest posts made by a user, where you need the user ID and the timestamp, you can combine 2 of these keys into a single key. So this would be a composite index where you have the partition key as user ID plus post ID. Now, if someone is looking for posts made by user number 6 with a time range of 60 to 90, they'll get the data quickly. So depending on your access pattern, you want to model the table accordingly. You can also add additional indexes. So for example, your sort key in the original table on timestamp works for one access pattern, but users may want to see the most popular posts ever made by them. In that case, you can sort by the like count. And if you get an incoming query of get me my most popular posts, you can get them quickly because of this new sort index. In this case, it would be a local secondary index. Amazon lets you use the same partition key with different indexes which are stored locally in the same partition. This keeps data strongly consistent and is sufficient for most use cases. AWS lets users make 20 local indexes on the same table. You can also create a global index. The main thing about this is you have a different partition key as compared to the original one. If you have user plus post in the original one, maybe a different access pattern is talking about get me all the comments for a post. So the latest comments for a post can easily be fetched if we use the partition key of comment plus post with the sort key of timestamp. In this way, you can see that a single table probably takes care of your entire application. The reason this is done is because you want to force users to think in the NoSQL term of key value pairs. You are okay with data duplication and denormalization, but you don't want to encourage joins at all. A caveat here is that the global index is actually an entire copy of the table. Amazon limits that to 4 global indexes, which is 4 additional tables. These are eventually consistent. The logs from the original partition are streamed to make changes in the global indexes. In this way, most complex access patterns can be resolved using a single table. Now, the last thing we should know about DynamoDB is that it has a concept of rate limiting or capacity booking. The basic idea is you only pay for what you ask. So let's say you want to read this data and each row is around 4 KB. Now, if you want to read this once every second, that would be 1 read capacity unit that you're consuming. So DynamoDB has these tables hosted somewhere. They know that the IO operations and the processing is going to take time. They understand that with 4 KB of data being read per second, that can be called a unit. So maybe one node can have 10,000 units, but a person doesn't come and buy an entire node. Maybe what they want to do is they say, I just want 100 RCU from this node. So if you take 100, it still has 9,900 RCUs remaining. This is maybe going to be used by other customers. So a single node can be potentially serving hundreds of different customers, different companies. Now, what you have to do is ensure that someone doesn't throttle everybody else. So a single customer who's asked for 1 RCU is now consuming 100 RCU is not acceptable. Everybody else will have to be throttled. So instead, what you want to do is throttle the person who's doing this. So DynamoDB gives you that 1 read capacity unit. If it sees that you're exceeding that, they go for throttling. Similarly, you have write capacity units, which is 1 KB of data being written per second. So let's say you book 100 write capacity units, and the node itself may have 10,000 or 50,000 write capacity units. Now, the sad part about this is whenever you're throttled as a customer, you don't like it. It feels unfair, or it at least feels irritating. So you want to avoid throttling, and especially you want to avoid unfair throttling. So let's say Zomato is using AWS and they have most of their traffic during dinner time and lunch time. So for 4 hours a day, they have enormous traffic of 500 RCU. 500 RCU Zomato, but yes, 500 RCU only. And the rest of the day, they don't have much traffic. During that time, they are using 500 RCU. The rest of the time, they are wasting this 500 RCU. Instead, the Zomato engineers, what they would really like is if throughout the day, they would have a more consistent RCU load of 200. Okay. But if they book this during lunchtime, you're going to exceed capacity. So they can either manually scale this down and scale it up during lunchtime, or they can just waste capacity. And this is not a very good experience for customers. Instead, what you want to do is you want to take care of this by yourself. You want to be fair. So if Zomato books 200 RCU, for a while, you actually start saving their requests. You start filling up a token bucket, which is the rate limiting algorithm in DynamoDB. And this bucket has 5 minutes of burst capacity. So 200 RCU in 5 minutes is going to have these many tokens, which is 60,000 RCU. Okay, let's say this gets filled up throughout the day, and then lunchtime arrives, everybody is booking lunch. From this bucket, instead of just being able to pull 100 reads, you will be able to burst up to 60,000 reads until you run out of tokens. So this allows the customers to leverage the wasted or saved up RCUs that they had from earlier. Okay, this is one of the reasons why the adoption rates are high. You can drop requests, right? What does it matter? But as a customer, it matters to you a lot. You feel like, oh, I paid all that money for 24 hours of this capacity, but I'm getting much lesser than what I had asked for. If you take care of that for them, they're already on your side. If you give them that bursting capacity, they're on your side. On AWS, this makes the challenge harder because you have this kind of bursting allowed for customers. You now have to find out the right distribution of data across nodes to allow this kind of burst for different customers. And in fact, AWS takes it one step further. This read capacity or write capacity that you have is set up across replicas. So locally, the throttling would have happened at 100 RCU itself, but instead now you have 300 across 3 replicas RCU. If one of the replicas takes 200 and the others take 50 and 50, that is going to be allowed. So AWS allow one to go to 200 without depleting your overall token bucket. So there will be no throttling as long as globally you're consuming less or equal to the amount that you have asked. So that's it for Amazon DynamoDB. I think this is a very interesting system because it's contrary in so many ways, but it allows transactions. It is very popular, but at the same time, it gives you a lot of control over what you want to do, and it behaves the way that you want it to behave. I think that's one of the major reasons why its popularity is so high. We also mentioned some of the crazy things that they did for allowing very high availability and predictable performance. Okay, Throughout Amazon's papers, you'll see that behavior of let's make boring systems, let's make systems which have predictable performance. If you have any doubts or suggestions on this, you can let me know in the comments below. If you want to know more about system design, then check out Interview Ready. I'll see you next time. Bye-bye.